All right, guys, welcome to our lesson on cartography. This is in our second unit, Mapping the World, and this one is all about how we make maps and how we read them. So here are the key questions that you'll need to keep in mind as we go through the lecture. First, I want you to be thinking about what are the things that make a map a map? What does it need at a minimum to be considered a map? The second question, what are the different types of maps? How are they similar and how are they different? The third question, why are different maps used for different purposes? And the last one, what are some ways that the three-dimensional world can be represented in 2 dimensions or in like the flat surface? All right, let's jump in. So making maps is also called cartography. That's just the fancy name for it. It's not just something that scientists do. It's an exercise in math, in art, in social science, history, and even more. Maps are important for politics. They're important for commerce or trading goods. They're important for so many things. There's a few different types of maps out there depending on what their purpose is. There's topographic maps, geologic maps, three-dimensional maps, and political maps. And we're going to get into some of these one by one as we go on. Now, all maps need a couple things. 2 of those things are legends and scales. So all maps have either natural or like geological or man-made features. So there may be a river that separates 2 countries from each other. There may be a mountain that separates 2 areas, or humans have created that boundary in between the 2 areas. So we represent all of these different features on the map using different symbols. So if you look over here on the right at this picture, you can see that this is the symbol that this cartographer decided to use for mountains. They use a dotted line to represent a road. They use little cloud-looking things to represent forests and so on and so forth. What this is a legend. That's what this is called. It's an area on the map that explains what all the symbols represent, what all the symbols mean. So let's move on to the next slide. So all maps must have a scale. And this is just a ratio between the actual distance and the distance as it is on the map. So what it's saying is, if you're looking at the map and you move 1 inch, how far did you travel in real life? It will help you when you're looking at a map to say, okay, is this a little hill that I'm looking at, or is it a big mountain range? There's 3 different types of legends and scales. There's verbal, there's graphic, and there's fractional. And we're going to get into what those are on the next slide. So verbal scales are the scale that is represented with a sentence or a statement. Verbal means to use words or to talk. So in this case, something like 1 centimeter is equal to 1 kilometer. That's going to be your verbal scale. So here's an example of a verbal scale. Sometimes maps may just have this. Sometimes they may have a combination of it and all the others. The next type of scale is the graphic scale. So this is a labeled line that's going to represent a specific distance. These are also examples of graphic scales. So what I can do is I can take this measurement and hold it up against my map and know, oh, that is about 60 miles or it's 100 kilometers. I can hold this distance up and I know it's 200 miles on my map. This is going to be one of the most common scales that you will see on a map. And the last one is the fractional scale. This one's for those people who really love math and maps. It expresses the distance as a ratio. So it's comparing what on the map is happening in real life. So this is going to be your map, and this is going to be real life. So these ones are really good if you have to calculate distances and you need more exact numbers when you're looking at things. But we're not going to use those ones nearly as much as the other two in this class. So all maps have one main problem. The Earth is round and a map is flat. So how can you represent curves and corners on something that is a flat surface? Well, scientists have figured out that the way to do it is using something called a projection. It's just a representation of the Earth's 3D structure using special lines or special shapes. There's so many different types of projections out there, and they all have a different use, a different purpose, and they all have different things that they focus on when they look at the Earth. So we're going to go through a couple of the main projections. The first, and probably the most popular, is the Mercator projection. So you make this one by essentially taking the globe and wrapping a piece of paper around it, where it's only really touching at one point. You don't want to wrap it around the entire ball. You just want to kind of make a cone all the way around, or not a cone, a cylinder all the way around it. So when you do this, it kind of distorts it. If you look here, when we're near the equator, one square is about that size. When you get up near the poles, look at the size of one square now. That is a huge difference. So with these ones, you're getting a very distorted Earth the farther away you get from the equator. So what are the pros and cons of this Mercator projection? Well, the bad thing about it, as I said, is that the longitude lines aren't going to be accurate. Normally they all curve inward to meet at the poles like they are here on this globe, but this type of projection can't show that, so we're going to distort the size of our land masses. Greenland is actually much, much smaller than Australia, but you wouldn't be able to tell that by looking at this map. So you're going to have issues with things looking too big or too small compared to other things. Now, what are the good things about this map? It actually is good to show the shape of the landmass. So that is the actual shape of Greenland, but it's not the right size. So this is good to help us see what the Earth actually looks like, what the US looks like, what South America looks like, etc. Now, it also shows directions in straight lines, so it's really good for navigating. It's really commonly used to navigate in ships and in airplanes. The next one is the conic projection. So you're going to actually make a cone and drop it onto the top of the Earth, kind of like one of those birthday hats, and you're going to just drop it on top of the Earth and turn it into a map. So if you see here, this is the, let's get a different color. This line right here is the top of the cone, and it's going to be rounded this way around the Earth. So this is made by placing the lines of the Earth onto a cone, and then you lay the cone flat. So the tip of the cone is almost always placed above one of the poles. You don't want to put it somewhere else. So it's always going to be the tip at the north or the south pole. So let's go over some of the pros and the cons of this. There's still some distortion. If we're looking here, here's one of the squares as we're getting closer to the equator, and here's one of them up near the poles. That is a pretty big difference still, but not nearly as bad as the Mercator projection. So this one's not good if you're going to be looking at large areas of land. You probably want to limit it more to like the size of a country, or like this one over here when you're looking at just a specific part of the moon. What are the pros? It's very, very accurate when you're mapping small areas. It's actually more accurate in the size and the shape of the land masses than the Mercator projection. So Mercator is good because you get the right shape, but not the right size. This one gives you a much more accurate size and shape compared to the Mercator. So when do we use these conic projections? We actually use them in road maps and weather maps, and to map very small areas. The next kind of projection is called a gnomonic. So it's kind of like a garden gnome. That's how you pronounce it. And what you're going to do is imagine placing a piece of paper just on top of your globe, just like this over here, where it only touches at one point. And then you're going to draw what you see onto the paper, kind of like as if it was a transparent piece of paper and you were going to draw on top of it. So it's really good when we're looking at the top of the Earth from the poles and looking down and seeing those land masses. So it makes all of your longitude lines seem like they're straight lines. Now, what are the cons of this? There's incredibly high distortion. I mean, look at these pictures here that are not taken from the poles. And you can really see how it's distorting the shape and the size of these land masses. So the pros, though, a line on this map shows the straightest route between two places. So it's good for long distance navigation, like pilots that want to go across the Atlantic or across the Pacific. So it's not good when we're looking at sizes and shapes, but it's great for traveling long distances because it shows you the shortest route between them. So what do maps tell us? Of course, we know that they have to have a legend and they have to have a scale, but what are the types of things that we're actually looking at or looking for when we're looking at a map? Well, one is elevation. Am I looking at a mountain? Am I looking at a valley, or is the land pretty flat? The next is soil type. So is it going to be more of a desert, or is it going to be a lush jungly area? What borders are there? Political borders, or is there a river that's bordering an area? What about the water? Where can I find water in this area? Water is essential to all life, so especially when you were one of the first explorers or settlers, you really wanted to know where those water sources were. Otherwise, you may not have survived. Then you want to know what you can see weather and climate patterns in a map. If I can see that Nevada is really dry and this area is very green and fertile, I can think that this area here gets more rain than the desert does. You can also see landmarks and other features like that. Now, one way that we can see all of this is using a topographic map. So this is going to detail all of the changes in elevation on the Earth's surface. So this is really good when we're looking at valleys and mountains, but surprisingly, it can also show you forests, rivers, and bridges as well, because they're going to be different than the surrounding areas. So we often use special lines, but you can also use symbols or different colors to represent changes in elevation. This one is just an example of using the lines. These lines are called contour lines, and they're used to represent different elevations at or below or above sea level, So they connect areas of equal elevation. They never cross each other, because if this line is connecting all the areas on the mountain that's 10 feet above sea level, it's never going to cross this line, because that line represents everything at 20 feet above sea level. You can't be at both 10 and 20 feet at sea level at the same time. So these lines will never ever cross each other. Now, contour intervals are the distances between these contour lines. How fast does it go uphill or downhill? Is it a more gentle slope, or is it really steep? If we have a tiny, tiny little gap between them, that's going to be going up in elevation very quickly. I go from 10 to 20 in a very short distance. But now this one over here, I go from 30 to 40 in a much, much longer distance. So that's going to be a nice gentle slope. The closer together they are, the steeper it is. The farther apart they are, the more gentle the slope is. Now, they also have lines on them called index contours, and these are numbers that mark what the contour line represents as the elevation. So this contour line here has an index of 700. That's probably like 700 meters or 700 feet. So sometimes there's only one index contour with a contour interval marked on the map, and you have to do the map to figure out the other lines. So for example, this one has many different contour lines, but only two have an index, 700 and 750. So you would have to figure out all these other ones, how far apart they are from each other. Well, we can see there's 1, 2, 3, 4, 5 spaces between, and we went up 50 feet. So these can each be 10 feet. So 710, 720, 730, 740, and 750. That's what we'd end up with. All right. The second thing that you need to be aware of on topographic maps are when we're going into a depression rather than elevation. So depression just means kind of like you're going down, or you're going into a valley. Think about if you're feeling depressed, you're kind of feeling down. If you're elevated and happy, you're going up. So an example of a time that we'll need to use a depression contour line would be like a volcano, where you're going up a hill and then all of a sudden it goes back down into the caldera, or the pit of the volcano. Sometimes you'll have a crater. Sometimes there's holes in the ground for some reason or another. And so we need to be able to tell someone, well, this contour line is going down, not up. So what they will use when they make these depression contour lines are these little marks on them all over here. Those are called hatchers. They're small marks on the contour line that will show you the direction that the hole is. So all of these are on this side of the line. So the hole is going that way. So this is going to be the deepest part. And this is going to be the shallow part, or the top. The first downhill contour line is always going to be the same elevation as the last uphill contour line. So here, see, we have a normal contour line at 20, and this first depression one is also 20. You have to know where you're starting to know where you're going to end up. If I just started writing 10, you wouldn't know when you started to go into the hole. It could have been over here. It could have been over here. But now I know by writing this contour line at 20, that's where the hole started, not this line that I'm erasing, and not this line. So it's just a way to make sure that you really know what you're looking at. So here are some more examples of topographical maps, and we're going to be analyzing these in our next class. So try to really go through this. If you didn't understand it the first time, go through it again, write down some questions that you have, because we're going to be going over this a lot. It's something that you're going to have to really understand, especially when we start talking about the weather. The more you understand it, the more you'll be able to get what we're talking about when we say weather patterns and climate and all of that. So another type of map is a geologic map, and these ones are used to show the surface geological features like fault lines, or if there's bedrock in an area, or what the soil type is. So this one will often use many different colors to show you what's going on. And so they'll have these really funny looking, colorful legends that explain what you're looking at. In this case, we're talking about different types of soil and sediments and what era in time they tend to be from. So what we use these maps for is to figure out what's happening underneath the soil. If I know what's going on geologically, I can gather information about what may be happening in the area that I'm mapping. These are often put with or superimposed, that means put on top of a topographic map. And why would you think that is? Try to think of an answer. Pause the video if you need to and try to think about why do we superimpose or put these types of maps on top of the topographic maps? Well, the main reason is because if you're looking at the type of soil and the type of geological features, you probably also want to know if you're looking at a valley or a hill. So it gives you a much better idea of what is happening to the land geologically. There's also three-dimensional maps. These allow probably the absolute best representation or the easiest view of the terrain, and they're made using computers. They're not easy to print out though, so it's very hard to actually get these to people unless you're on a computer. So these ones are really great, but they don't travel well. They're not good if you need them in the field. So let's summarize everything that we just talked about. All maps need a legend and a scale. All maps are going to have some problem with what we call distortion, because we're trying to make the three-dimensional globe of Earth into a flat piece of paper. Not everything, not all the curves are going to transfer over well, so we have to make projections, and there's so many different kinds. They allow us to represent the curvature of the Earth in different ways. Every type of projection map has some kind of fault in it though. They have good uses and they have limitations. Topographical maps are special maps that use contour lines to highlight the changes in elevation, whether you're going higher or lower from sea level. Geological maps show us the different types of rocks or geological formations and help us figure out what is happening underground. And finally, three-dimensional maps give us the best view of the specific features of the land, but they're hard to move around. So this is a good table to study from. It tells you what the map or the projection type is, what are its common uses, who uses these mostly, what are they good for, and how are they distorting the Earth? How is this projection falling short? So I would turn this into some kind of study card or put them on note cards, print it out, whatever you need to do, okay? Now, I want you to think of any questions that you may have and come prepared next class with those questions because I want to go over them with you. And we will do some practice with reading topographical maps and even making them next class. Hope you guys enjoyed it. See you soon.